Hello. So, let's talk about um, curve sketching. Now, I did a video on this before, but because I didn't get a good graph, didn't really like it. So, we're going to use all our skills for the next, from all the curve sketching, or from all the first derivative tests and the second derivative test, all that stuff for curve sketching. So that way we can do some cool curves. So let's pick, I'm going to pick an easy function, and it'll be just a little mini thing. So let's pick a function. And I'm going to pick an easy one just to demonstrate curve sketching, because I don't want to do some weird ones. So let's do x to the third plus x squared minus x. Clearly an easy function to look at. And I want to sketch this function very accurately. And what I want to do is I want to use my tests. So for curve sketching, so I'm going to use a lot of things. I'm going to list them out. You got to write that down in your notes. So let's list all the things that we need to draw a curve. Well, we want to find some symmetry, maybe. We want to find some intercepts. We want to find intervals where a function's increasing, when a function's decreasing, when we have concavity. We want to find relative extrema, and then we're going to find points of inflection. So this is all the stuff we need to find. Well, let's look at symmetry. If we plug in negative x, we get out, we don't get out our function, and we don't even get out the negative version of our function. So we don't have symmetry, or we don't really have the symmetry we want. But, so I'm not going to really use symmetry right now, because it's a polynomial. We know it's a polynomial. So let's use intercepts, increasing, decreasing, concavity. So the first thing I usually want to do is I want to set up my first derivative test. So I want to find all the critical numbers. So if I find f prime of x, that's 3x squared plus 2x minus 1. And I want to solve that for 0. When is that equal 0? Well, okay, I can figure that one out pretty easily. Okay. So we have an intercept. So this equals 0 at x equals 1/3. not x-intercept, sorry, are critical numbers. So x equals 1/3 and x equals -1. So our critical numbers are -1 and 1/3. And we want to test the first derivative. We want to plug in the numbers. Now there are some things that we do want to look for, like asymptotes. But we don't have asymptotes because we have a polynomial. Okay. So let's plug in points that are on these intervals and see what kind of things we have. Like, do we have extrema and stuff like that? So if we plug in -2 into the function, or into the derivative, to find out the sign, we get a positive number. If we plug in 0 into the derivative, we get a negative number. And if we plug in 1, we get 3 plus 2, which is 5 minus 1, so we get a positive. So, ooh, wait. So, we're increasing on the intervals from -infinity to -1 and from 1/3 to infinity. Right there. We're decreasing between -1 and 1/3. Ooh, we have relative extrema. Remember, it's changing from increasing to decreasing. That means -1 is a relative max. So, max at, and we want to plug in -1 into the function. So if we do that, we get -1 plus 1 is 0 minus -1, which is 1. So we have a max at this point. From decreasing to increasing, oh, that's a relative min. And we have that at 1/3 comma. If we plug in 1/3, it's a little bit of a tougher one. We get negative, I'll put it into decimal form, negative 0.185. Okay. Can we find the second derivative? Yeah. That's 6x plus 2. When does that equal 0? Well, that's equal to 0 at x equals -1/3, right? Well, that's a potential point of inflection, right? So a potential point of inflection at, it's over here, -1/3. We're going to have to test for concavity there. Okay, so let's do that. So let's plug in something like -1 into the second derivative. If we do that, we get a negative. Let's plug in 0 into our second derivative. We get a positive. Wait, we changed concavity. So we're concave up from -1/3 to infinity. And we're concave down from -infinity to -1/3. And we have a point of inflection at x equals -1/3. We have no asymptotes, do we have any intercepts? We should, right? Let's set the function equal to 0, right? We can factor out an x. We get x squared plus x minus 1 equals 0. So x equals 0. And how about this equals 0? When is this equal to 0? Can we factor out? Let's see if we can factor that. So, let's see. It's kind of a tough one. We can't really factor this. But we have a 0 there. And we have a 0 over here. So, okay, we got intercepts. X equals 0, 1 plus root 5 over 2, and 1 minus root 5 over 2. So we kind of got all of our information jumbled up. This is all the information we have. So we have so much information now. It's kind of cool. So now we're ready to graph the curve. So let's do that. Let's graph it. I'm going to put these in decimal form. So 1 plus the square root of 5 over 2 is 1.618, right? And the negative one would be negative 0.618. So these are really close. So if intercepts at 0, negative, so it's really, really close to here, but let's put this as 1, negative 1, and 1. So this would be kind of right here, and this one would be right over here. Okay? So we're concave down, but we're increasing. So we're going like this. And we have a max at 1, right? So we're from, well, no. Oh. Hold up a sec. We're increasing concave down. Hold up. We have an issue. Hold up a second. So I had an issue with the zeros. Sorry. The intercepts were negative 1.618 and the positive one is 0.618. So that kind of makes more sense, right? So it's over here, right? And then the next one's like right here. So we were increasing in concave down, and we have a maximum of negative 1, 1. So we're going to go up like this, right here, that's the maximum. And then we're decreasing all the way up to 1/3, right? We'll be decreasing all way to 1/3. Didn't really do this. So we had an increase. Oh, we had a maximum at -1. There you go. And we went up and all the way down. This is not up to scale, that's why it kind of looks really weird. I'll pretend it's up to scale and I'll do this kind of stuff. Like right here. See, 0 should be all the way over here, but it doesn't matter. So, it's decreasing and it's still concave down until -1/3, where we have our point of inflection, which is right here. And then we have a minimum at -1. Oh, it's somewhere like there. That's our minimum. At 1/3. Now we're increasing after that. And there you go. And then you go concave up from there. So that's kind of what the graph looks like. Of course, it's not up to scale. But you can plug in points and make a more accurate representation of that. But this is what we kind of wanted with curve sketching. That's our goal with curve sketching. Now for the next 10 minutes, I'm going to talk about problems that involve minimizing and maximizing stuff. Because that's kind of what our deal was. Our deal was, wait, we have a curve. When do I hit a maximum? When do I hit a minimum? And there were problems, or problems in real life, where we have minimum, and maximum issues. So things like, hold up. Like, hey, we have a box. We have a cube box thing, but we have a box. Okay? And I want to produce a maximum volume. This is length x, this is length x, and the h is the h. So we have this issue. So there's kind of a box right here. And this is length h, so you know what that is. So the question is, hey, I have a surface area of 108 square inches. I want to make a box that has a surface area of 108 inches. Okay, it has to be, I have to use up that much material, 108 inches. But I want to maximize my volume. I want to fit in the most stuff with certain material, limited amounts of cardboard or something like that, right? That seems like a reasonable problem, and we have to understand how to do it. So we gotta create a function and actually find where its maximum is. That way we can figure out the maximum volume with limited surface area. So what is the volume of the box? First of all, what's the volume of the box? Well, the volume of the box is x times h. So it's x squared h. That is the volume of the box. But we want to find the maximum. And if this is a function of two variables right here, and we can't really have that in these kinds of problems. We need a function of one variable and finding out where that maximum is. So we have to kind of relate h and x. We have to substitute h for x's. So it says surface area equals 108 inches. What is surface area? Well, this is x times h, and how many sides that has? 2, right? I believe 2 sides. And 1, 2, 3, 4 sides of x times h. So it's really 6hx, right? So the surface area, so the area of this is h times x. The area of this is h times x, right? So it's a box. Yeah. So it's 6, isn't it like 6hx? 6h or xh equals 108. And if we solve for h, we get h equals 108 minus 6. Sorry. 108 over 6 pounds. Oh, what's this area? X squared. So sorry, guys. I'm sorry. So the bottom side is not hx. So it's the area of 1, 2, 3, 4, 5. So the areas of these 1, 2, 3, 4 are h times x. For xh plus x squared equals 108. There you go. Sorry, this is weird. And the box has a lid. So the box has a lid. It doesn't have a lid, sorry, it's an open box. That's why my surface area is off. So the box is open, so it's just that. That's why. So h would be 100 over 8 x squared over 4x. We substitute that for h here, so we have volume equals x squared over 108 minus x squared over 4x. There you go. So now, okay, we can kind of simplify this. V equals x over 4, because the x squared cancels out, times 1 over 8 minus x squared. We want to kind of make this a polynomial. So 1 over 8 divided by 4. 1 over 8 divided by 4 is 27. So we have 27x minus 1/4 x to the third. That's kind of our equation. We want to take the derivative because we want to see if it changes. We want to set it equal 0 so we can see what's the maximum volume. Derivative would be 1 over, negative 3/4 x squared, that's this part, plus 27. We're going to find where that equals 0. We have to find where that equals 0. So that equals 0 at 6 and negative 6. So equals 0 at 6 and negative 6. You can solve that on your own, right? And, okay. So, let's make a little thing. V prime. Right over here. So V prime, and then we'll put two numbers. 6 and negative. Oh! Can the volume be negative 6? Nope. Can't be negative. So we just need the two sides here. So now we have to plug in something less than 0, or not less than 6, and something greater than 6 for the derivative of the volume. So let's do that. So if we plug in something like 1, so negative 3/4 times 5 squared plus 27. So this is positive. And let's plug in 7 into the derivative. So it's 3/4 times 7 squared plus 27. This is going to be negative. We have an increasing to decreasing, and that's a maximum. So the volume is going to be a maximum when x is going to be 8, as x is going to be 6. So the dimensions, x is 6, and if we plug in all those, if we find h, that's going to be 108 minus 6 squared. And then divide that by 4 times 6. Sorry. Divide that by 6. Divide that by 6. And h has to be 3 to maximize our volume. So here are the dimensions we have to have in order to maximize the volume. And that's what maximizing and minimum problems have to do. So let's review. So I have an open box, right, with these dimensions, x and h. And I'm trying to find the maximum volume with this surface area. So we have to maximize the volume. How do we maximize? How do we find a maximum? Well, we do this first derivative test, right? We take a derivative. But we had to relate because we have x's and h's. So we have to relate h to x and plug in that, take a derivative, find the critical numbers, test them, and if we have a maximum, we know that x is going to be 6, plug in 6 into h and find the dimensions using that. And that is maximizing and minimizing problems.